Hello, my name is Melissa Sartinornat, and welcome to another episode of our MAE speaker series, Industry Insights from Gator grads. Please let us know where all of you are joining us from today in the YouTube chat. Today, we are joined by MAE alumni Dr. Giselle Fernandez. Giselle is a postdoctoral research associate in the Verification and Analysis Group, Computational Group at Los Alamos National Laboratory in New Mexico. Her research is currently focused on machine learning applied to fracture mechanics and inertial confinement fusion. Giselle earned her bachelor's degree in nuclear engineering from the Instituto Balseiro in Argentina in 2014. She earned her master's and doctoral degrees here in MAE under the supervision of Dr. Hafka and Dr. Balachandar. Her research focused on multi-fidelity surrogates and uncertainty quantification of large-scale multi-phase flow simulations. The presentation today will be about 30 minutes, followed by a Q&A, so be sure to post your questions in the chat window at the end of the talk. And with that, I hand off to Giselle.
Thank you, Melissa, for your presentation. I'm very happy to be able to be here to share my experience with you. Oh. Hi, everyone. I think you weren't able to hear me because my mic was mute. Sorry about that. So I'm very happy to be here sharing my experience as a graduate student, but also as a postdoc student, postdoc at the national laboratories. And thank you to Dr. Hafka that recommended me for this presentation. So with that, I'll start. So I entitled these presentations, Data Science Insights from Los Alamos National Laboratory. And I'm in a group that is called X Computational Physics. This is the division, and the group is called Verification and Analysis. So let's start. So this is an outline. So I'm from Argentina originally. I went to college there. And then I'll talk a little bit about my experience in college. Then I'll talk about how I end up at UF and my research at UF. Then I will give some tips and recommendations that are based on my personal experience that you might find useful. And then I'll talk about, the national laboratories, because thanks to my experience at UF, I was able to work closely with the National Nuclear Security Administration national laboratories, and I'll talk a little bit about that. So let's start. So I'm from Argentina, especially I was born in Cordoba, which is here, and I went to college in the city. The city is very beautiful. I include some pictures here. This is the city from the top, and then this is the river that is called the Cañada, and it's a very old city, but it has its charm, and it's very European. And I went here at university, so in Spanish would be Universidad Nacional de Córdoba, and where the major here that I pursued was physics and mathematics from 2009 and 2011. After that, I moved to Bariloche to pursue nuclear engineering. That was the major. And Bariloche is in the south of Argentina, and it's very, very beautiful. I include some pictures. You have the mountains, and then everything is green. I don't know how that happened. It might be a microclimate or something like that. And then you have a lot of lakes, and I've been in multiple places around the world, but Bariloche, I think it's one of the most beautiful places I ever been. And I went here to Instituto Balseiro, and I got my degree in nuclear engineer. And I was there from 2011 to 2014. So in this university, this is a very renowned university, and one of my professors from Instituto Balseiro put me in contact with Dr. Balachandar at the University of Florida. And that's what my journey begins. So I contacted Dr. Balachandar by recommendation of my professor. And at the time, in 2014, he got a very large grant from the Department of Energy. So he was excited to bring students, and after we had some conversations, he asked me to join the team, and I was very pleased about that. And so my advisor, so my chair was Dr. Hafka, and then Dr. Bala was my co-chair. And at University of Florida, I got my master's in mechanical engineering in 2016 and my PhD in 2018. And at UF, I had one of the best time of my life, and go Gators! So now I'll talk a little bit about my research at UF. So I joined to the CCMT in 2014. The CCMT is the Center for Compressible Multiphase Turbulence, and it was funded for 5 years, and it started in 2014. And this project is called PISA-2, which is Predictive Science Academic Alliance Program. And it was the second, so they had the first edition, and it was the second edition. And the video that you are seeing on the right, it's a multi-phase detonation. So you have particles confined in a very small cylinder. And after detonation, you can see in white the glass particles, and then there are steel particles that in the boundaries, and that's why you see the lead. And this piece of project gave the center the opportunity to make research, so do research in this about this problem, which is a very complex problem because you have a lot of physics playing at the same time. And the idea was to be able to use simulations in order to predict this behavior. And so the money came from the Department of Energy, in particular from the National Nuclear Security Administrations. And the project was the Advanced Simulations and Computing. And we were involved, so there were 3 main laboratories involved, which was Los Alamos National Laboratory, Lawrence Livermore National Laboratory, and Sandia. And so the idea of this project was to do or to pursue predictive science based on verification, validation, and uncertainty quantification for large scale simulations. This is something that is very important in these national labs because they work with very dangerous and very expensive systems. So you want to quantify your uncertainties, and you want to validate your codes in order to be able to assess the problem. And this was an excellent opportunity for me in order to collaborate with a lot of physicists, engineers, and data scientists. And I had a great experience. And here I include a link to the center, the CCMT at UF, so you guys can go there and check it out. So this is related with what specifically I've done. So again, the video. And my thesis was at intersection of the flow of physics, various large scales multi-physics simulations, surrogate models, optimization, and uncertainty quantification. And the main goal was to study and characterize how initial perturbations in the particle phase evolve at later times. And so the main tools that I used during my research was RockFlu, which is an hydrocode that was used by the center initially. Then they shift to CMT-NEC. But at the time we were using RockFlu, And I also had the chance to work with supercomputers, mainly from Lawrence Livermore National Laboratory, because in order to do my research, I need to run a lot of simulation to have like a statistical representation of the problem, and also to get enough samples from building surrogate models. Then I use a lot of MATLAB. I started using Python, and right now it's the main tool I use at the National Lab. So I would recommend you guys to, if you don't use it, just start to try it out. It's very similar to MATLAB. So if you're using MATLAB, it won't be like very hard shift. And then another thing that it was very useful for me was self-scripting for automation, because we needed to run multiple runs, so to be able to automate the process was helpful. And then for visualization, we use ParaView, which is a free software, and then we use TechPlot. And my main finding was that initial concentration of particles dictate the particle's trajectory. And here I include some results of my main, so this is my main result from the investigations that I did at the University of Florida. For example, these are the simulations, and in the left we have the initial time, and we have this particle volume fraction quantity, which is particle volume fraction measure how many particles you have in comparison with the particles and gas in a cell. And this is at initial time. So you see that you have radial regions with more particles, and in blue with less particles. And this is a sinusoidal web. And we realized that after, this is the final time, we actually simulate short periods. This was at 500 microseconds. And we saw that this initial perturbation in the particles translate and perturbations in the position of the particles. And I study also, well, this project was challenging because we needed to find a way to quantify all those things. How you quantify the perturbation amplification was challenging, but it was a great way to learn. And for example, this is the measure that we built, and this is showing how the perturbation amplifies as a function of time. And so here I'll try to give you my personal experience, and I hope that, and some tips, I hope that helps. For example, something that I would suggest, everything that, this is for graduate students. So everything that you, every time that you write a paper or a draft of the paper, a good practice is to send the paper to the authors you cite, right? This is a great practice for two reasons, because you get the feedback from them. So you say, you receive their ideas, and also if they are happy with it. And then also people is aware of your work. So they are actually know that you're working on that. And then they can potentially cite your paper, or invite you to conferences, or to give you, to give presentations for your work to be more known, to share your work. And then another thing that this was one of the most important for me. So do your best, but you shouldn't stress out. So for example, in my experience at the beginning, I wasn't able to give a lot of results. So I wasn't being able to deliver much. And I guess my advisors were kind of like frustrated about my, I don't know, my performance. And I don't know, like, well, I keep doing my best. And at the end, so after my PhD, I was able to get 5 papers. So 4 was peer review, very high impact papers. And one review paper, it's an archive. And the interesting thing that they were all published the last years of my PhD. So don't get frustrated if you cannot publish the first year, or you cannot write or find anything interesting like the first time, during the first years of your PhD. You just keep the good work, be positive, and do your best. And that's the best you can do. So don't get stressed out. Another suggestion that I would give is answer your emails fast. At the beginning, I was very, very bad at this, and and Dr. Hafka teach me that lesson. So he was very, very good to answer the emails. So you could send him an email and he will answer 5 minutes after with like 3 paragraphs. I don't know how he would do that. Anyway, I'm not asking you to do that, but at least email. So you need to answer them anyway. So just do it fast, and that will help you to. So that will help to the fact that people will be happy working with you because you are responsive. So that's another recommendation I would give. And then other important thing is context. Context in your field are invaluable, so you need to create them. So so you can make context in conferences. I also made context reviewing papers, because when you review, you get to meet the editor and other people, the person that is submitting the paper, and the co-author. So that's another way to do it. Also recruitment events. So there are many ways to do that. And why you want to do that? Because first of all, you meet people, you have a great time. Then these people can help you to find jobs. Why? Because like so they get to know you, and they know that that you're doing a good job. And then if this is a good match, they can recommend your work in their organization or in their industry. Then also can help to get letters of recommendations, and also if they know your work, they can cite you. So that's a win-win for everyone actually. And then the last tip I will give here, it's fight imposter syndrome. So I didn't know that this thing existed until last year when I went to a conference, and there was like a talk about this imposter syndrome. It seems like a lot of people feel like they don't deserve what they achieve. And I felt so identified by what this person was telling, and I saw that everyone was actually kind of identified with this. And it's something that happened, but it's not true. So every time that you think that you don't deserve it, or you are in this position because of luck, because you were in the right group with the right people and they help you, and it wasn't because of your own merit, just ignore that, because that's not true. You are in the position you are because you are very good. Okay. And this, as I said, this is the list of publications that came from my PhD. If you see, they're all from the year I graduate, or actually after the year I graduate. So don't get too stressed out about that. And now I'll talk about a little bit about my experience in the national lab. I'm a postdoctoral researcher at Los Alamos National Laboratory, but I will talk a little bit about the 3 NNSA DOE lab. NNSA stands for National Nuclear Security Administration, and there are 3 main labs working on this. One is Los Alamos. Los Alamos is located in New Mexico, in Los Alamos, that's the city. Then you have Sandia National Laboratories, and laboratories is plural because there are 2. One is in New Mexico, in Albuquerque, another is in California. And then the third one is Lawrence Livermore National Laboratory, which is in California. And the mission of these national labs are to get a reliable United States nuclear stockpile through the application of science and technology. this national lab have a lot of funding. So the science that is being developed here, it's mind-blowing. And then the other mission is to prevent nuclear weapon proliferation and reduce the threat of nuclear and radiological terrorism. And in my experience, the PISA project allowed my research to be known by influential people on my field working at the national laboratories. And why? Because they would come every 6 months to see our progress and to give us recommendations. So, and also I got to go to Sandia for an internship. And after graduation, I got an offer for a postdoc from Sandia, and also from Los Alamos, and I chose Los Alamos. I wanted to have like a more diverse experience, so that was part of the reason. And so what can I say about being a postdoc at Los Alamos? So you have freedom, because what I'm saying this because like it's very different. You usually have 3 options when you finish graduate school. So you can go to industry, you can go for academia, or you can go somewhere in between, which is a national laboratory, right? So as a postdoc at XCP8 is, my division is computational physics, and 8 is the verification and analysis group, which is my group. And I feel that I have freedom to make my own research and to get involved in more than one project. And for me, that's very important, because when I get stuck, I can switch my mind to another topic, and that helped me a lot. And then when I come back to the other project, I feel that I have new ideas, and that helps. And then also, I got to know and work with amazing physicists, engineers, computer science, statisticians in the most complex and challenging and exciting problems that I ever worked. This is, all the problems are very multidisciplinary, and the environment is very friendly. Being a postdoc at the National Laboratory is great for your CV, and the salary is good if you compare with other opportunities, so I would recommend it. So, so my background, in particular at CCMT, I work at the intersection of physics and uncertainty quantification. So I can summarize my expertise as surrogate modeling, verification, validation, and uncertainty quantification, and data analysis. So due to this expertise, and also by the fact that people from the national laboratories were like teaching us, and they were like coming every 6 months to tell us what would be something that we can work on or develop our expertise on, I was of the interest of them. So, and I was invited by LAN to accept a postdoctoral opportunity working in machine learning. So at the time I was very excited, and it blew my mind. Actually, I really like working in that. And since I'm here, I work in 2 projects. One project is fracture mechanics, where we seek to inform continuous scales models with crack evolution to improve their fidelity and maintaining the low cost. So the important thing is you get accurate results with cheap simulations. And then the other project is inertial confinement fusion, where we seek a better understanding of the relationship between the design inputs and also with the outputs. And this is in order to make better predictions and also augment expert intuition. And I'll talk briefly about the first project, which is a project in collaboration with a lot of people, as you see, and that's the best part. That I found that very fulfilling. And the title is Flyer Play Continuum Simulations Informed with Machine Learning and Crack Evolution. And the motivation for this work is there are some continuous models that they're cheaper than, for example, finite element, discrete element ones, but they don't simulate cracks, right? And for brittle materials, we are interested in brittle materials. And for these materials, it's challenging to get good predictions without actually simulating the cracks. So we use a higher fidelity called HOS, which is a finite element, discrete element code, which is very expensive to train neural networks. So we can inform this low fidelity and reduce cost while maintain accuracy. And this is a little bit the workflows. As I said, we have flag and then host, and then we inform flag through machine learning. And our goals were to upscale flag using host, but also accelerate host via machine learning, because host is so we using machine learning will reduce 4 orders of magnitude the cost, right? And I would not want you to get lost in this slide. This is only the main result. Here was the validation, what we wanted to accomplish, and we actually did, and we recently published a paper on this. So we had the experiments, which this is the wave velocity, the shock wave velocities through the material, right, as a function of time, and we had some experimental data. We see that hosts, which is the high fidelity, were able to match the behavior, right? To have this bouncing because the cracks were present, so the shock wave will bounce. However, flag it wasn't able to replicate this result because the lack of crack modeling. But the fact that we build this machine learning give us the accuracy of host or similar, right, in red at a very low cost. So that was a good project, and we are at the end of this project, and we have a couple of simulations, 1 paper and 3 presentations, and there was one where I was nominated as a rising star in computational data science, so I was very happy about that. However, because of the coronavirus, the presentation was pushed to the fall, so we'll see what happens. And then the second project is called using machine learning techniques to study plasma fusion experiments, and this is also in collaboration with amazing people. And this project, we are just starting. We got experimental data from the NIF. NIF is the National Ignition Facility, and it's located in California in the Lawrence Livermore National Laboratory. And I included some pictures from this is the target chamber, and here you see the target assembly. And everything is happening here. It's a very small device. This is actually 1 centimeter. It's a very small setup. And well, this is an instrument to measure quantities of interest. And the lower part of this slide show a little bit what is the inertial confinement fusion approach they use at the NIF. So it's called Indirect Drive. And what they do is, so the laser beams hit the Horum surface. The Horum, it's a gold cavity that holds the pellet where you have the fuel for the inertial confinement fusion reaction. And usually it's deuterium tritium. And then when the Horum get hot, emit very hot because of the laser beams, emit X-rays, and hit the pellet as if it were direct drive, but actually they are coming from the Horum. And then there is an implosion of this deuterium tritium capsule, which gets to very, very high densities and temperatures. And after that, there is plasma ignitions that yields many times the input energy. So it's very efficient. So that's why we are very interested in this reaction. And the project overview that I'm working right now, we have a high dimensional experiment data set. We have 26 design inputs and 1 output. And these were experiments that were like conducted from 2011 until 2019. So no surrogate model is best for every situation and for every data set. So we need to choose the best for this particular set. And we did it while testing multiple options, and the performance was chosen for the performance on the test data, which is the data that the students haven't seen. And then a part of the project was to use machine learning to interpret complex coupling between the inputs, right? Because understanding the relationship between inputs can help to assess correlations and have a better prediction. And then we have importance of variables. Important is something somehow equivalent to sensitivity analysis. So you are assessing how important is each variable to predict an output of interest. And we did that also with the principal components that sparse PCA gave us. And then we also assess the surrogate performance of both the design variables and also the sparse components. And then the future work, because as I said, this is just starting, is to combine experiments and simulations. And the object is validation, and then also consider other outputs. Right now, the output that we consider is neutron yield, but total yield is called actually. And but there are many others like as temperature, velocity, and somehow a lot. So I don't want you to get scared by this slide. It's just like the main findings that we got. And the only thing that I'm showing here, these are the sparse component weights. So each component, it's a combination of inputs, right? And we found out that most of the inputs are very related in a physical way. For example, these inputs are all coming from the whole room. These are coming from the capsule. These are coming from the laser, which was a good finding. And also here I show the importance of each of these components. For example, we get to know that the number of pulse steps of the laser will give us one of the main components that help us to predict yield. But then the second important is the peak power and the laser energy. And this gives us insight in the physics, which has been very neat. And I really like this project. And we just started, but we got to present in the BMB symposium. And well, our postdoc that I'm commenter her, she got the student poster presentation award, and she got the second place. So we are very happy about that. And I guess this is one of the most important slides I have, not only because it's the last one and you're happy to be able to leave, but because I include a message from my division leader. So, so he sent this message. So we're always looking for outstanding candidates for our student, postdoc, and early career staff pipeline who can enhance our team environment and who will help us contribute to the computational physics side of Los Alamos National Laboratory's national security missions. We have formed a relationship with faculty at the University of Florida, and we hope to continue with our campus visit once travel restriction is a bit. So we are actually visiting University of Florida once a year, and we are happy to get to know you. And if you're interested in working with us and you think your background is a good fit, we will be happy to receive your CV and talk to you. So you can send me your questions and to my email, but also I included Mark email. He's the division leader. He's very busy, but I'm sure he will be very happy to have to answer your email as well. So I include it here. And with that, I will take questions and I will say thank you to all of us, of all of you. Yeah.
Thank you, Giselle, for the wonderful presentation. And I'm glad to hear that Los Alamos is hiring at UF. So now we're going to answer questions from the audience. So please do post your questions in the chat box now. Giselle, I was wondering, as you were showing like some of those experiments, like for the computational component of this project, how closely do you work with the experimentalists, or in this type of project, is it kind of all separate type of divisions? I'm just curious a little bit about how, I guess, it all comes together.
Yeah, well, that's actually a very good question, because each laboratory works a little bit different. For example, Lawrence Livermore, it's I guess because it's in California, they need to reduce the space, so they are very they are located together, so it's not as hard as us. So Los Alamos, it's very spread. So people from experiments will be like some miles away, right? Like, so like in that sense, it's hard, right? Like we are not sitting in the same building. We have like a lot of buildings, and actually, but we do a very good job with emails, right? And the good thing is people here is very responsive. So when you, so maybe you don't know like how to get an experiment that you are interested in, but then you start contacting people until you get that information, like, is this experiment exist, right? If it does, who is the person to contact? And then also you can ask them a lot of questions, right? Like, for example, how uncertainty we can quantify, why you don't report uncertainties, what are the conditions of the experiment? Like, this is very, you can do it, and it's encouraged to contact people from the lab and ask you questions, and they're very collaborative. So in that sense, it's not very bad. Actually, it's very good.
That's good to know. We do have a question from Professor Steve Miller, and his question is, do you have any advice for graduating PhDs entering a research organization?
So a research organization, does he mean a national laboratory or in general?
I'm gonna guess a research focused place. Yeah, like a national lab. Let's go ahead and interpret it that way.
Okay,
and these are interesting times to be looking for a job as well. So I don't know if you have any added spin on that as well.
This is challenging. Actually, right now I'm in the process of converting to staff, and I've been looking opportunities all around, and it's a difficult time because people a lot of effort in the labs or I guess in other organizations as well to be like try to handle this situation as best as possible, right? And then they need to organize how people will work remotely, or so they're like their focus is more on organization right now. However, for example, we still are hiring. For example, in that regard, we are doing interviews using virtual tools, but there. So in my search, so I contact some industry, and most of them told me like, so like right now, like we didn't post anything because we are focused on trying to figure out this situation. But going more directly to the question, so I don't know. I think you need to be. I guess the smarter way that I would go for an application in a research organization would be find a posting that match your background and try to assess. So you will have always like a part in the posting that it will give you like the minimum requirements or desired requirements, right? And you need to tackle those, right, in your CV. So the person don't get lost in your CV. So, try to include that in your expertise. Try to tackle those things right away. So the person who is looking at it, that person could be a human resource person, right? So you need to make yourself appealing to them. So I would say that you should build your CV for each particular posting. Just for example, and a strategy is that just change your expertise of course, need to be true, but saying directly based on their requirements, I would say.
I think that's wonderful advice. I don't know that students are sometimes aware of that you do need to tailor your cover letter and resume and CV for whatever job you're posting for to highlight aspects of your strengths that they're looking for.
Exactly.
We do have another question, which is great, from Professor Doug Spirat. He says, hi, Giselle. What do you think is the best way to learn machine learning, surrogate modeling, PCA, and other data science methods coming from a computational physics background?
Oh, that's a good question. Actually, well, that was my experience. So at the beginning, I would say, at the beginning was challenging for me because I didn't know anything about surrogate model or anything, right? So during my PhD, my expertise became in surrogate models. So I started with regression, linear regression, Bayesian based models, right? But then I realized that the world or the community is changing to looking more in machine learning. But machine learning definition is, it's sometimes like not very clear, and it depends a lot in which people you're talking to. For example, in my opinion, machine learning is anything that you can give data to a computer and the computer is able to predict a condition that it hasn't been he hasn't been informed to do, right? Like, so it's outside of the training data. And, but that's a very broad definition, right? That involves all surrogate modeling like rigging, Bayesian-based, linear regression, random forest, but also neural networks and deep learning and all this thing that is commonly referred as machine learning. So if that is the definition that we're using about machine learning, I would say, in my case, when I arrived to the lab, they want me to work in recursive neural networks. And at the time, I barely had any experience with neural networks. So, and I was the first person in the project. So it was very challenging. So what I did was, I did a lot of I self-taught myself through internet, like, and starting with very easy test problems, like toy problems, similar to the problem I was trying to solve, and then try to, from seeing that, I started like to go deeper in the code, right? Like to see what exactly was going on. Some surrogates as neural networks are really hard to see. They're really a black box, right? You don't understand what is going on there. That's why it's very challenging. Me coming from linear regression, that I know exactly what I'm doing, was a very challenging thing to do. So, but I guess I did it like by myself. And also, well, in the lab you have a lot of support. So I took a Python course on machine learning. So they taught me a lot of different things. I'm also using PyTorch. I'm using mainly PyTorch and there are two main, Keras and PyTorch, that both are built in on TensorFlow. However, they are easy to learn. So I would recommend for beginners to focus on Keras and PyTorch. And also, like, you have so many things online. I would say that, yeah, the internet is a very great place to go to get informed about, yeah, machine learning.
It is a good point. Like, once, you know, when you have your PhD, people expect you to be able to learn new topics, you know, rigorously, and you know how to learn.
Yeah, and also I would say like papers help me, like research papers in the topic help me to figure out which kind of surrogate model I would choose. For example, what if convolutional neural network or recurrent neural network. At the beginning, I was so new at that. So I would go to the literature, and then when I point, okay, this might work, right? Like this seems to be something that it might work in my problem. Then I got my hands dirty and I started trying to, yeah.
Okay, so we have more questions. So from Professor Scott Banks, he says, thanks so much, Giselle. We have many students from all over the planet that are interested in the kind of work you describe. Can you talk about how the US national labs work with foreign nationals?
Yeah, that's a very good question. And I would say that Los Alamos is the most open to foreign national. However, it's not easy. So I would say that it's a good approach is to have a contact there, right? Like, or have a very, very good match with the research, right? Because in my experience, they are being like very, so the first reaction I get from them is we cannot hire foreign national. And then when they get to know you and they get you know your work, they start like figuring out ways to do that. It's not that they cannot hire foreign national, it's so complicated for them. They need to justify why they're hiring a foreign national instead of an American. And also, most of the, for example, I'm in X computational physics. That means that my work, it applies to weapons, right? And it's highly classified. So, and I'm working there. However, my work, it's not classified. But sometimes it's not so easy to make that division, right? Like between works. And they usually require that you have a clearance. And in order to have a clearance, you need to be a US citizen. But I would say in order to get a position or an opportunity in a national lab, you need kind of have contact. However, for students, it's way easier. If you're looking for an internship, it's not as hard as it were for a staff position, right? But it's not, so I would say it's easier for Americans, yeah.
But not impossible. Case in point.
Here.
But that's it. I have a related question from Dr. Bala. We want to continue to recruit outstanding students from Argentina, especially from Bariloche, to our PhD program. What should we do?
Bala, that's an excellent question. Remember, I contacted Dr. Mariana Cantero, and I think like we need to, I'll check those emails again, and we will try to keep the conversation, because I don't know what happened when we haven't continued maybe, well, with the coronavirus outbreak and everything got delayed, but you're right. So I'll definitely help you with that. Today I'll check those emails and I'll send a reminder so we can start looking for a student from Argentina.
On behalf of the Graduate Recruitment and Admissions Committee, we thank you. So the next questions, these are back to a different topic, but from Dr. Bruce Carroll. What types of problems or applications do you see yourself working on 5 years from now? And what are the new issues on the horizon that you see?
Okay, that's also a good question. So right now, there is a lot of funding for machine learning. I see that a lot. And in particular, in my division, so it's verification and analysis. So right now, I'm starting to look for opportunities due to this option for me to get converted to a staff scientist. in working on verification problems. So verification, I would say that you can describe it as to check if you if you implement your equations right in your code. And I'll start working on that, on finding an analytical problem to test our hydrocodes. That would be something that I think I will be involved in the future. Also, I want to keep my machine learning focus. So I think that the possibility for me to keep working in the inertial confinement fusion project are high. Like I think that would be something that it would interest me. But also, I think in the future, I would also be interested in I don't know, more like a manager position or something like that. So we are starting talking with my manager about those things, which is something nice that I didn't know that we could do at an entry level like me, but she's very nice. And we discussed about these opportunities, and she gave me some advice. And I guess after I got my citizenship, because I'm in that path, I'm about to get my green card. So I guess in some years, if everything goes the same as it has been, I would be able to have a clearance. And then I don't know, I would like to be more in the intelligence part of the lab, which is very, I find it very interesting, the problems that they solve. So that would be something that I see myself doing. Yeah.
Lovely. So we have another follow-up question, and it's related to that. So based on it, and it's follow-up to Doug's question, should we be offering undergraduate courses to introduce machine learning, given, you know, how important it is?
Given? Sorry.
Well, I'm just saying, do you think it'd be a useful skill for our students that we graduate?
Oh yes, definitely. So now, like, especially at the national laboratories, there's a lot of focus on, so what my perception is, before they were like building this huge, very expensive hydrocode. However, now there are a lot of push for uncertainty quantification, and in order to be able to assess uncertainties, you need to have multiple simulations, also for optimization problems and everything, and that's very expensive. So the focus is to get, I would say, cheaper ways of prediction, and also for when you need to give an answer very fast, and you say, okay, like I have this tool, so machine learning can help to give an answer, which is, it's a good answer. You have like 90% of accuracy, let's say, but it's like order of magnitude cheaper. So yeah, I would say that it's a skill that it would be very valuable in the national labs, at least, that I know. Yeah.
Okay, thank you. The questions keep coming. So Dr. Chen, she says, hi Giselle, may I ask you why you chose a fracture project while your PhD training is in something different?
That's a good question. Actually, when I was offered, so I had two offers, one from Sandia, which was working exactly in what I was been working before. And then one from Los Alamos that was to work in this fracture mechanics. And I wasn't very sure at the beginning. I said, oh, this is so different. So during my nuclear engineering studies, I did, so my thesis was a surveillance program, which we assess how the concrete material for the pressure vessel reacts to radiation. I did some material fracture studies, but it wasn't my background. However, my manager told me, look, this is so having skills in material fracture, it's very good for you, because it's something that there are not many people working on it, and it's very useful. Like you will always need someone that tells you how the materials react to different loading conditions and temperatures, so on. So she convinced me that it would be good to work on that, and then I learned a lot. So it was something new for me. But then I got to, as I tell you, like, this is very flexible, and you get to work in many different projects. So I saw this inertial confinement fusion, and I asked her if I could join, and she said, yeah, you can work on that too. And then you get to go to the side that you like the most. So yeah. My postdoc was a decision. When I decided, it wasn't easy, because one opportunity was exactly what I was doing, and the other opportunity was everything was new. The problem was new. I didn't have much background with neural networks, so I said, "Oh my God, like, what should I do?" And then, well, I like challenge, so I went there.
Well, I know everyone appreciates you telling people, giving insight into how you make your career choices, because, you know, everyone has to make, you know, at these critical junctures, you know, what's right for them. It's always people make different choices. Exactly. So I was gonna, you know, sometimes it's something new, it's something the same. Okay, so then we have, I think this might be one of the last questions, if not the last question. It's a student. He or she is interested in one of the summer programs at the lab, specifically something called LADSS. I'm not sure if you're familiar with it, if there are any students here this summer or not, but maybe last summer. But do you have any advice for applicants such as this student who's interested in a summer internship? Okay, I think it's probably an undergraduate, maybe a graduate student, not sure.
I see. Well, I didn't come here as a student, so I'm not exactly sure. Unfortunately, I don't know about this particular project, but you have my email in the slide. I'm not sharing the slide, but you can send me an email, and I can look for it. But as recommendation, so if you like computational physics and you think your background is along with that, I would say contact us. We are always looking for a student, and I would suggest contact the person. So the lab does a very good job in their webpage in posting the interest and the different divisions. And I would say look for the scientists and just bug them, like sending an email, say, look, my name is Giselle, like, I'm interested in this and I'm interested in that. I saw that you are interested in having students for coming in the summer. I don't know how the thing is working right now. I think they're trying to implement a virtual program, but this won't be forever, right? So, I'm pretty sure the things will improve. So I would say, well, apply to in the regular way, but don't be shy to bug them directly. I think that it's nice to receive an email from a student that is interested in your projects. Don't think that's a bad thing. Okay.
Great advice. Okay, this is the final question, and it's from Herman. And you'll see, like, in our department, we have a lot of interest in machine learning. So he's wondering, was there any particular website that was more useful than others for understanding machine learning?
That's a good question. I usually, there is one that usually solved my question, which is a Stackflow, something like that, which is the TensorFlow question part, because that you have the TensorFlow. I'm talking about kind of neural networks, right? And the TensorFlow, you have the documentation part, but there's like the questions part. And usually I find there this particular question that, oh my God, how can I do this? Or how can I like choose a better option for that? And usually that's the web page I use for particular, but I cannot tell like a single web page that it will give you all the answers. Like actually, I couldn't say that there is one.
Okay, thanks, Giselle. And thank you for the time that you took to put together a presentation and to present to our department. I know everyone appreciates it.
Oh, thank you so much, Melissa.
Of course. And so at this time, our presentation and discussion comes to a close. We want to thank all of you for attending, asking questions, and staying engaged. We'll be launching another episode of this MAE speaker series next week. So please be on the lookout for that. It'll come in your email. And have a great day, everyone.
Bye. Thank you for coming.